Hi, my name is Imran and I will be presenting to you the topic for my project, Development of Graphical User Interface for Commercial Software to Determine SRV Dimension and Permeability by using 3D Partial Differential Equation Solution and Microseismic. Feel free to pause at any time of the video in case you need to read anything in detail. The outline for the presentation will be as the following. I will be explaining to you the research background, problem statement and objectives, scope of study, research methodology, the novelty or the significance of this project, results and discussion, as well as a video demonstration of the software to the conclusion and recommendation. For the research background, unconventional gas reservoirs has been increasing in its importance towards the energy industry. Looking at the chart on the left cited from Annual Energy Outlook 2016, the trend of the natural gas consumption is forecasted to be a steady uptrend and could reach up to almost 35 trillion cubic feet per year. The chart on the right shows gas production from several types of unconventional reservoirs, and it is forecasted upon the year 2040, almost all the gas production will be from unconventional reservoirs. So, what are actually unconventional reservoirs? Unconventional reservoirs are reservoirs that do not have the permeability enough to economically produce the well. Thus, the reservoir needs to have artificial or induced permeability and conductivity. The ways to produce these reservoirs economically are either by production from horizontal wells to maximize the area connected to the reservoir, or hydraulic fracturing to create conductivity and increase permeability, or multi-stage completions, or all mentioned. The most common practice in the industry is to have multi-stage horizontal hydraulic fracturing. To measure the efficiency of the hydraulic fracturing operation, a method called microseismic monitoring is used, where the microseismic events data is translated into stimulated reservoir volume, or SRV, which is the area of the reservoir being fractured that creates conductivity. The figure on the right is the real figure from a microseismic events data captured in this case study of the project, which is in Alberta, Canada, which include 12 stages of hydraulic fracturing. As mentioned, the SRV is an indication of the hydraulic fracturing operation efficiency. Since the original condition of the very low permeability unconventional reservoir could not give us economic production, the SRV is assumed to be the new reservoir volume, and production will only take place in the stimulated reservoir volume, or the SRV area. The microseismic events data indicates on the fracture size, hence indication for the SRV dimension. The chart on the right shows that the larger the SRV dimension, the larger the production will be, and leads to higher productivity of the reservoir. Next are the objectives and the problem statement. The problem statement that leads to the project are the need for a more efficient method for the SRV dimension and isotropic permeability prediction before hydraulic fracturing operation commences, and there is a lack of user-friendly graphical user interface that is straightforward and easy to use softwares in the market for the SRV dimension, as well as permeability values determination of this hydraulic fracturing operation. As for the objective of this project, they include the need to solve SRV dimension and permeability values in a more efficient way, and also to create a graphical user interface, or GUI, that is user-friendly and straightforward to be used for the hydraulic fracturing design. Moving on to the scope of study for this project, it involves the study of 3D linear diffusivity partial differential equation, the study of Python programming language to create the software, and also the case study of this project, which is a tight gas sand reservoir in Hoadley Field in Alberta, Canada. Next, the novelty or the significance of this project is that this project is aimed to optimize the efficiency of the hydraulic fracturing operation, mainly by reducing the time spent and also reducing the cost incurred. Time spent is reduced by having such simple and straightforward graphical user interface for the software that easily gives out the most important output, which are the SRV dimension and anisotropic permeability. Whereas the cost can be significantly reduced by eliminating the need to have microseismic observation for reservoirs that exhibit close to similar reservoir properties. Besides, hydraulic fracturing simulation softwares out there in the market are not as simple and straightforward like mine, as users need to attend several days course in order to learn how to use it. Furthermore, some of the softwares in the market do not even give out the output either the SRV dimension or the anisotropic permeability simultaneously. Now, this is the research methodology. It starts with the understanding of the 3D linear diffusivity PDE equation derivation before developing the GUI for the software. Basically, this equation will be the equation that governs the entire calculation to determine the SRV dimension as well as the permeability values. a code for the equation of diffusivity coefficient that is an important parameter for the calculation, as well as the equation to determine the SRV dimension and permeability values, are written into the software. User input is tested with the case studies microseismic data into the GUI. The software will then implement the coding written to find the best line slope that covers at least 90% of the data below it, as studied by Urbansik and Bake in 2013 mentions that a valid SRV requires at least 90% microseismic event. The software will run a loop to find the best line slope that covers at least 90% of the data. The line slope is then used to determine the diffusivity coefficient, that is a very important parameter needed to solve for the SRV dimension as well as the permeability values. The software will then solve for the results of the SRV dimension and permeability values, and the output will be displayed in the GUI. Users then can view the illustration of the SRV dimension map generated from the GUI. As mentioned, the first step is to understand the equation derivation of the 3D linear diffusivity PD equation solved by Dr. Yu and Dr. Aguilera to be utilized for the calculations to determine the SRV dimension and the permeability. It started with the general nonlinear diffusion equation in x, y, and z direction. This equation can be rearranged and simplified by assuming the insignificance of nonlinear terms, which leads to the representation of the fluid injection induced pressure difference to a location in a porous medium, and delta P injection is the fluid injection induced overall pressure difference to the porous medium. The equation can be simplified into the next equation, where the symbols that looks like the alphabet N represents the diffusivity coefficient. This equation undergoes separation of variables and can be solved by assuming Pn xyz equals to uxt, vyt, wzt. This equation will undergo Laplace transformation and can be expressed to the final solution, where the diffusivity coefficients in three directions are as the following. This equation can be rearranged to find the permeability, which is the kx, ky, and kz in respective direction. The approximate solution can be applied to represent the pressure front that triggers microseismic events during reservoir stimulation. Rearranging the final solution gives three equations which the SRV dimension in three different directions. Notice that in both SRV dimension and permeability equation, it involves the diffusivity coefficient or the N-like symbol parameter, hence it should be determined firsthand. The next step is to create the GUI itself. The figure shows that the coding was started with importing several libraries into the body of the GUI. This needs to be conducted in order to set up the GUI window. The imported libraries are the first line of the coding, which are the import Qt GUI, Qt core, Qt widgets, which are meant to include the necessary functions that the GUI should display, perform, and assist respectively. In the second body of the coding, it is the GUI initialization with the numerical function to work with user input numerical data. The user input data, which include the porosity, the viscosity, the values of the pressure triggering difference, and the pressure injection difference. The compressibility is initialized as float character, considers decimal points, so that there will be no error in the calculations. The GUI is also programmed to only accept user input that are non-negative values and only numbers with no alphabetical characters into the user tabs. Other than that, the coding also requires some special libraries to be imported into the GUI to perform complex mathematical operations, such as the calculation of the SRV dimension equation. That includes the error function. The code is shown in the fifth line of the coding, which are the from SciPy import special. Lastly, the GUI window is self-setup by including the second body of the coding, which is the self.setup UI in bracket self and self.retranslate UI in bracket self. The GUI will look like the following, where it will have the input section for the users to load in the data file, as well as the output section where users can view the results generated. Next is the diffusivity coefficient determination. This parameter requires for a slope line from the microseismic data that covers at least 90% of the data below it to be included into the solution to determine the diffusivity coefficient. Rearranging the SRV dimension equation gives out the equation to determine the diffusivity coefficient in all three different directions, which are XYZ, or north, east, and that direction. These equations are then translated into coding language into the software as the following. The software will run the calculation based on the coded equations once the software has found the best line slope of each hydraulic fracturing stage for every direction that is needed for the calculation. The same goes to the SRV dimension determination, where the equation to determine the SRV dimension is being coded into the software. Again, the software will run the calculation based on the equation coded, but this time it is once when the diffusivity coefficient has been calculated, because there is diffusivity coefficient in the solution. Next is to test on the user input. Users are required to input the microseismic data into the GUI in a specific Excel format, which is, for every stage data, it should be segregated into a different tab. For this case study, which is having 12 hydraulic fracturing stages, thus the Excel file need to have 12 tabs segregating the stages. The user then loads the microseismic data with the correct format, and a successfully loading message will appear on the GUI. The user needs to click on the Generate and Save Charts button for the software to find the best line slope that covers at least 90% of the data. This is the coding that programs the software to find the best line slope. What the code tells that the software to do is that the software will find the most extreme data point, which are the most right data point for the x-axis and the most top data point for the y-axis. From these two data points, the data point of the x-axis is extrapolated upwards and the data point of the y-axis is extrapolated to the right until the extrapolation intersects. The intersection is then connected to the point 0, 0 of the data and a line is generated. The GUI will calculate how many points are below the line generated just now to determine whether the line covers at least 90% of the data or not. If not, the software will increase the line slope to 0.01 every time until the line slope covers 90% of the data, and yes, it will run in a looping manner. For example, as the figure, this is an example of the line slope for stage 1 in the direction of depth or Z direction. The software will generate the best line slope for all the 12 stages in all 3 different directions for each stage, meaning the software will generate 36 line best slopes that will be used to determine the diffusivity coefficient. Next, after the value of the slope for each line is determined, then only the software can calculate the diffusivity coefficient, since the solution for it requires the slope value. Again, the equation of the diffusivity coefficient is translated into coding for the software to run the calculation. The rearrangement of the diffusivity coefficient equation will give us the solution for the permeability values in 3 different directions as the following. And again, these equations are coded into the software for calculations. The same goes to the equation of the SRV dimension, where the software will run the calculation based on the coded equations in 3 different directions. To recap, the overall flowchart of the SRV dimension and permeability values for each 12 stages of every direction goes as the following. User input the microseismic data, software finds the best line slope, software calculates the diffusivity coefficient, and lastly, software calculates for the SRV dimension and permeability values for all 3 different directions for each stage for 12 stages, totaling up to 36 values of SRV dimension and permeability values. This is the milestone or Gantt chart in doing this project. Most of the time is used to learn on the coding and programming using Python programming language. Moving on to the results of the discussion, I'll be mainly highlighting on the outcomes of the successful codings which enable the software to operate and to function properly. This is the result for the GUI creation. The GUI window has 2 different sections, which are the input section and the output section. The input section is for the user to load data and to input field parameters, while the output section is for the user to view the results of the SRV dimension and the permeability values. After the user input microseismic data, by clicking the Load Data button, a successfully loading message will appear and prompts the user to click the Generate and Save Charts button for the determination of the best line slopes to commence. This figure shows an example of the successfully generated line slope, for example, for stage 1 in that direction or in Z direction. For the software to calculate the SRV dimension and permeability values, user needs to input on the field parameters, which include porosity, formation compressibility, hydraulic fracturing fluid viscosity, as well as the delta P triggering and the delta P injection. For this case study, which is in the field of Alberta, Canada, the field parameters are as the following in the table given. The user can key in the field data into the input section and the GUI should look like this. Users need to click on the calculate permeability and the SRV dimension after done inputting the field data to get the SRV dimension and permeability values results. The GUI will then finally show the results of the SRV dimension as well as the permeability values in X, Y, and Z direction. The SRV dimension and permeability values are the average from the 36 values of SRV dimension and permeability values respectively. The results from this GUI for this specific case study shows that the permeability in X, Y, and Z direction, or east, north, and depth direction, are 0.9258 millidarcy, 2.3553 millidarcy, and 0.0584 millidarcy respectively. The result for the SRV dimension, on the other hand, in X, Y, and Z, or east, north, and depth direction, are 307.4 meters, 470.1 meters, and 77.87 meters respectively. The user then can click on the Generate and Save SRV Dimension Charts button to generate the SRV dimension maps for illustration of the SRV. These are the examples of the SRV dimension maps generated. The map is generated by finding the midpoint of the data, assigning it to be the point 00 and plotting the SRV dimension distance from the midpoint. For example, SRV dimension for stage 12 in east direction is 395 meters and for the depth direction is 37 meters. Looking from the figure below, which is the depth versus east direction map, from the midpoint for x-axis that accounts for east direction, a point approximately 150 meters to the right and to the left from the midpoint are plotted, giving 395 meters distance. And for y-axis that accounts for the depth direction, a point approximately 20 meters above and below the midpoint are plotted, giving approximately 37 meters, and those 4 points are connected into a diamond shape to illustrate the SRV dimension. Users then can view the overall values for all three directions for each stage for 12 stages by clicking the View Results table button. A new window will pop up and display all the values. The GUI windows should look like this. This tab displays the slope value results. This tab displays the diffusivity coefficient value results. This tab displays the SRV dimension value results. And last but not least, this tab displays permeability value results, all in 3 directions for each 12 stages. The following will be a short live demonstration of the software. Hello and welcome to the live software demonstration. So this is the software. I just currently call it as Hydro just for simplification. So let's open it. It will take some time to open, so please be patient. Now, this is the GUI. So, the first step is I have to load my Microseismic data file into this GUI. So, let me choose my Microseismic data file, which is in the correct format, which is required from the software. So, my data file is this one, right? So, a successful message will appear and it will prompt the user, which is me, to press this Generate and Save Charts button. But before I generate and save chart button, I have to create a folder for me to save the charts. So let's just create and call this folder as chart 1. Right? So let's generate and save charts and save it into the chart 1 folder created just now. So the GUI will generate and save the charts into this chart folder created just now, and there we go. So the chart generated is the Microseismic event data together attached with the baseline slope for every 36 charts that covers at least 90% of data. So as you can see here, this is a chart for stage 1 in that direction. So stage 1 in that direction looks like this, and it covers 92% of the data. For stage 1 easting or X direction, it covers also 92% of data, and so on. Stage 2, that is north. Stage 3, that is north, and so on until stage 12, right? So there are 36 charts in here. So now let's put up our data field, our field data into this GUI. So as mentioned, the data is as below, right? So the porosity is 0.15. The delta P triggering is 0.03 here. The delta P injection is this one, 18.62. The viscosity in CP is 30. And the compressibility is 5.81 times 10 to the power of -4. Right, so this is the field data that user needs to input. And to find or to determine the SRV dimension and also the permeability values in 3 directions, user need to input this calculate permeability and SRV dimension, and this software or GUI will straight away give you the answer. See? So in this case, our case study, the permeability of the SRV is 0.9258 millidarcy, 2.3553 millidarcy, and 0.0584 millidarcy in respectively X, Y, and Z direction, or east, north, and that direction. As well as for the SRV dimension, for the X, Y, Z, or east, north, and depth direction, respectively, the results are the 307.4 meters, 470.1 meters, and also 77.87 meters. So now, as we have gotten our results, which are the dimension, SRV dimension, and also the permeability, now let's press this button and generate our SRV dimension charts. But before that, we have to create another folder for us to be able for us to save the charts in a more organized way, right? So let me just create folder. So let's just name it as chart 2, right? So let's generate and save the dimension chart into the newly created folder, chart 2. So select folder, and the progress bar shows the progress of the dimension chart generation. So your dimension charts have been saved. So to view, just simply click and open the folder, and you can view all the 36 charts, SRV dimension charts, right? So for every stage, it will consist of depth versus east, depth versus north, right? And also north versus east. So this is for stage 1. These are the illustration of the SRV dimension maps. Stage 2, stage 3, depth versus east, stage 3, depth versus north, stage 3, north versus east, and so on until the 12th stage, right? The totaling of 36 maps. Thank you. As per conclusion, the project has successfully improved the hardware manufacturing operation by optimizing the time span. Furthermore, this project also is projected to significantly reduce the cost of the entire hardware manufacturing operation, mainly by eliminating the use of the microseismic well observation, typically to close to similar reservoir properties. With this case studies one. This project also has successfully created a very easy, straightforward, and user-friendly software that enables users to quickly predict and determine the SRV dimensions and anisotropic permeabilities given the field data and parameters. So I can say that this project is this software is unlike any other software out there in the market. As per recommendation, it is recommended to have multiple data from various fields so that this software can be tested for its capabilities. Second recommendation is that for the software to be cloud-based so that this software can be updated by the developers when improvements and maybe new features come along the way. Thank you.